Hello everyone, the topic for my today's presentation is physical vapor deposition for the synthesis of nanoparticles and nanomaterials. So I'll start with the presentation. So for the synthesis of nanoparticles, basically there are two main approaches, that is the top-down approach and bottom-up approach for the synthesis of nanomaterials and nanostructures. In top-down approach, a suitable starting material is reduced in size using mechanical and chemical means, and bottom-up approach refers to the building of structure by atom and molecule by molecule or cluster by cluster, as we have discussed in the physical classes. Then in this, initially the nanostructured building blocks are formed and subsequently assembled in final materials using the chemical or biological procedures. So the main topic for my today's presentation, that is the physical vapor deposition. So it is also called as PVD, is one of the bottom-up approach. The physical vapor deposition is a process of transferring growth species from a source or target and deposit them on a substrate to form a film. The process mostly involves no chemical reactions. Various methods have been developed for removal and for growth species from the source or target. The thickness of deposits can vary from angstroms to millimeters. In general, those methods are divided into two groups, basically, that are evaporation and sputtering, which we'll be discussing in brief. Then PVD is characterized by a process in which the material first of all goes to the condensed phase, as it's shown in this diagram. So first of all, it's the source material is going to the condensed phase, or that's the solid phase, by first converting into the gas phase by the process of evaporation, and the transport and deposition of the gas phase is done again, in which we are getting the condensed phase once again. Then so it's back to the thin film condensed phase at the last, and each group can be further divided into a number of methods depending on specific techniques applied to activate the source or target atoms. Now discussing for the inert gas condensation, which is the PVD method or the physical vapor deposition method, with additional feature of using the inert gas to reduce the mean free path of the species. It is commonly used to synthesize metallic and metal oxides nanopowders with a narrow particle size distribution. In this process, a metal is evaporated inside an ultra high vacuum chamber. So as it's shown in the diagram, this is a ultra high vacuum chamber in which the evaporation of source is taking place. So this ultra high vacuum chamber is basically filled with the inert gas. Typically argon and helium is used as an inert gas. The source of vapor can be evaporated by the sputtering target or laser ablation target. The vaporized species then loses the energy via collisions with inert gas molecules. So basically why we are using the inert gas molecule to lose the energy of the vaporized particles, and as they lose the energy, the collision takes place. So as collision limit the means free path, supersaturation is achieved above the vapor source. At supersaturation, the vapor rapidly form a large number of clusters that grow via agglomeration. Then the cluster in the condensing gas are transported by the connective flow to a vertical cold finger surface filled with the liquid nitrogen. So this part, the finger surface is filled with the liquid nitrogen where the agglomeration or the condensation is taking place. They are collected via funnel and transported to an in situ compensation device or coated with a surfactant agent at the last to prevent their agglomeration. The scraping and condensation of particles are carried in the high vacuum to prevent the oxidation of the metallic nanoparticles. Now it's very much important for us to control the size and morphologies, and yield of the nanoparticles is to be controlled. So they are basically dependent on the three fundamental parameters by which it's controlled. So the rate of supply of atoms to the region of supersaturation where condensation occurs. Then the second is rate of energy removal from the hot atoms via the condensing gas medium, and third is the rate of removal of clustered once nucleated from the supersaturated region. So basically this method, the inert gas method, has some disadvantages also, like the formation of clusters and large size particles are taking place. Then it's very expensive process also, and the yield also per batch is very much low. Now coming to the evaporation techniques, so it is basically the simplest deposition method and has been proven particularly useful for the deposition of elemental films. In this, the system consists of an evaporation source that vaporizes the desired material, and a substrate is located at an appropriate distance facing the evaporation source. Both the source and the substrate are located in a vacuum chamber. The substrate can be heated or electrically rotated during deposition. The desired vapor pressure of source material can be generated by simply heating the source to elevated temperatures, and the concentration of the growth species in the gas phase can be easily controlled by varying the pressure and the source temperature. Okay, so this diagram is showing it that the source or the substance is kept in this boat, and the evaporation is taking place, and it's at the fixed distance, and it's taken down in the vacuum chamber, as I have told that we need to prevent the oxidation of gas. And then at the substrate it's condensing. Here evaporation is taking place, and then it's condensing to form the thin layer. The equilibrium vapor pressure of an element can be eliminated by this formula, that is ln Pe is equals to minus del He upon Rgt plus C, where ln Pe we are calculating, that is the equilibrium vapor pressure, and where minus delta negative is taken, and minus del He is the molar heat of evaporation, Rg is the gas constant, T stands for temperature, and C is the constant. Now evaporation techniques basically is of two types, that is the thermal evaporation technique and the electron beam evaporation technique. Now what's happening in the thermal evaporation deposition is inside a vacuum chamber, where the material usually in a boat is heated typically to its melting point, and the substrate to be deposited on its is positioned facing the source. Okay, and the high current flowing through the boat heats up and causes the evaporation, as it's seen in the diagram, that here the source is evaporating due to the thermal procedure, the heat, the particles are evaporating, and at the substrate the condensation is taking place and the deposition of film is taking place. Similarly, in the electron beam evaporation, the technique is based in the heat produced by the high energy of electron beam bombardment on the material to be deposited. A high DC voltage is applied to a tungsten filament that causes the electrons to emit out, and these emitted electrons are accelerated to excite the target solid and produce vapor which travel to the substrate, and the same thing is happening as it was in the thermal evaporation, that the condensation is taking at the substrate film. But in this one change is there, that the evaporation due to the electron bombardment, the evaporation is taking place. The common uses of this method are, this is used for depositing material with very high melting point, that is tungsten, carbon and tellurium, etc. And it has some limitations also, that is very high temperature process is required, and ultra high vacuum of 10 to the power 4 torque is required, and one of the great disadvantage is that the cost cutting is very high for this method. Now coming to the molecular beam epitaxy. Molecular beam epitaxy is a special technique for epitaxial growth of material under ultra high vacuum conditions on the substrate surface. The growth occurs by the interaction of molecular beams from two or more beam sources at the substrate. It is generally used to deposit elemental or compound quantum dots, quantum wells and quantum wires in a highly controlled evaporation of variety of sources. Now as shown in this figure, a typical MBE method, that is a molecular beam epitaxy, is set up consists of 3 vacuum chambers, that is the load chamber, the transfer chamber, and the growth chamber. This entire is a growth chamber in which the growth of particle is taking place. The growth chamber consists of evaporation cells, reflection, high energy electron diffraction gun, that is also called as RHEED, RHEED, and detector, mass spectrometer, and few more parts. The substrate in the substrate, the RHEED is used to monitor the growth of product, that is the RHEED, that is the reflection high energy electron diffraction gun, is used to monitor the growth of product. The main attribute of molecular beam epitaxy are a low growth of temperature, that is 550 degrees Celsius is required for gallium arsenic, that limits the diffusion and maintain the hyper abrupt interfaces, which are important in fabricating the two-dimensional nanostructures. Then a slow growth rate that ensures a well controlled two-dimensional growth, and a very smooth surface is achievable by this process and technique. Similarly, a variety of in situ analysis compatibility provide invaluable information for the understanding of this process. Now coming to the sputtering process. Sputtering is to use energetic ions to knock atoms or molecules out from a target that acts as one electrode and subsequently deposit them at a substrate acting as another electrode. Okay, so basically 2 electrodes are used in the sputtering, and from the one electrodes the bombardment of inert gas particle is happening, due to that the ejection is taking place, and on the another electrode the deposition is there, the deposition of thin film is taking place. So shortly saying, super deposition are methods of depositing thin films by sputtering. They involve ejecting materials from a target, that is a source, onto a substrate such as silicon wafers. Atoms of target source material are ejected or sputtered by high energy ion bombardment of high energy noble gas atoms, commonly which are the noble gas which is used commonly is argon gas, produced by high voltage DC or RF glow discharge. And these ejected sputtered atoms from a thin film coating after condensation on substrate at anode form a thin film. So here is a diagram of the film growth which is shown. So by the DC sputtering process, which includes the first part. The first part includes the migration of single atoms to the substrate. The atoms are migrating. Then the aggregation of the single atom is taking place in the second image. Then the nucleation of atom to form the nanoparticles. Here the nanoparticles are formed by the nucleation of atoms. Then after the nanoparticles are formed, the growth of nanoparticle is taking place by an agglomeration of nanoparticles is taking place at last. And in the last process, what's happening after the agglomeration, the thin film is obtained at the substrate. Then there are some of the advantages of this sputtering method, that is this technique doesn't require high thermal process heating, and no heating is required in this process. Then it works at very low vacuum as compared to the evaporation process, and it's also having some limitations, that are the controlling deposition parameter is very much difficult, and similarly it's also a high costing process. Then the last process, the laser ablation technique. In this method, a solid metal rod is ablated using a high power laser in a chamber containing argon gas. In the plasma that results from the laser ablation, metal atoms are evaporated and condensed on water cooled substrate. And this technique is basically used for formation of nanoparticles of iron, gold, palladium. Compounds of silver are also produced by this method. So looking at the diagram, so here the laser is bombarded on the target, and due to this that the ejection is taking place, and on this substrate it is a water cooled substrate, so the condensation is taking place at this level. Okay. Now it is having some advantages that are that it is capable of high deposition rate of 2 to 3 gram per minute, but on the other hand it is a high temperature method and a low quality material is deposited, which are few of the advantages or disadvantages of this technique. Now there are some sorry. So there are some major difference between the evaporation and sputtering, that are the deposition pressure differs noticeably, that is the evaporation uses typically high ranging pressure from uses typically low ranging pressures from 10 to the power minus 3 to 10 to the power minus 10 torr, whereas the sputtering requires a relative high pressure of 100 torr. Then in evaporation, atoms and molecules are not collided with each other, but in sputtering the collision is taking place. Then the evaporation is process describable by thermodynamic equilibrium, whereas the sputtering is not. The growth surface is not activated in case of evaporation, whereas in case of sputtering the growth surface is constantly under electron bombardment, and thus it's highly energetic. The evaporated film consists of large grains, whereas the sputtering film consists of smaller grains with better addition to the substrate. So the PVD, that's the physical vapor deposition coating, are generally used to improve the hardness, increase wear resistance and prevent oxidation. Thus such coatings are used in wide range of applications, which are aerospace, then architectural panels and sheet, then on automotive it's also used, then dyes and molds for all manners of material processing. It's also used on cutting tools, fire alarms, optics, watches, jewelries and many more applications are also there. And these are my references for the presentation. Thank you so much.